Hello world. If you have been practicing deep learning for a while, you may have been using optimization algorithms like gradient descent with momentum, RMSprop, IDGrad, and there are so many optimization algorithms, but I'd like to talk about all the mathematical intuitions which goes behind RMSprop, and if you haven't used it, you'll get a better idea of what it really does and whether you are implementing in TensorFlow or Keras, what's actually happening. So one way of visualizing it is when we use any optimization algorithm while training neural network, we want it to go slower in the vertical direction because the actual learning part is happening in the horizontal direction, and we want to damp out the oscillations which are happening in the vertical directions, so that you see this red dot in the center, that's the optimum and which we are trying to reach, and we want our function to converge at this point. So it would be really faster and efficient if we are able to traverse faster in the horizontal direction and damp out the oscillations in the vertical directions. And when we are running it in a batch, what we want to do is we want gradient to be big in the direction in which we want to travel in a small distance, and gradient to be small in which we want to travel larger distance. And similarly, in the vertical direction, we want learning to be slower, and in the horizontal direction we want it to be faster. And so we want to move quickly in the directions with small but consistent gradients. Know that gradient should be consistent, and move slowly in the directions with big and inconsistent gradients, that is in the vertical direction. So to give a better intuition, let's say that our parameter w is in the horizontal direction and b bias vector, it's in the vertical direction, and so on every iteration we are going to be computing dw and db back propagation, and we want learning to be faster in the horizontal direction and slower in the vertical direction. And so from it's analogous to exponentially weighted averages, and know that we are using a different notation which we had used in gradient descent momentum so that you don't get confused. And so STW is going to be equal to beta times STW plus 1 minus beta times dw star stars 2 or maybe whole square, and note that this is element wise squaring, and so we are keeping our exponentially weighted averages of the square of the derivatives. And similarly we are computing SDB is equal to, which is equal to beta times STB plus 1 minus beta times dB square, and then we are going to update our parameters which are w and b. So w is going to be equal to w times minus w minus alpha times, alpha is the learning rate, dw over under square root of STW. And similarly we are going to be updating b also like we do in gradient descent, but it's the notations and the powers which are doing it are different. So in RMSprop, and the reason why it's called RMSprop is first we are squaring up the gradient term, and then we are dividing it by the square root of STB and SW. And one thing which you need to know is this term over here, dw square, it's gonna be small because we are traversing in the horizontal direction and we want it to be small, and db is a large dimension vector and it's gonna be large. So updates in vertical direction are being divided by much larger number, so b over here, and STB it's gonna be large because db is large and the square of it is also gonna be large, and we are dividing updates in vertical direction by much larger number, and then we are damping out the oscillations in the vertical direction. So updates in vertical direction are divided by a much larger number. And if you were try to visualize it, as you can see this green line over here, what's happening is we are able to traverse faster in the horizontal direction, and that would enable us to converge at the global optimum at a much faster rate. And note that this W and B are use this notation to give better intuition, but in practical aspect, if you try to visualize it, these W's and B are very high dimensional vectors, and in the vertical direction you're not gonna be using W, it's gonna be B, it's gonna be B1, B2, B17 and on so on. And so these are high dimensional vectors. So if you were to implement in Keras, we're gonna import this model from optimizers, and then we are going to create a sequential model, and then we are going to create a dense layer using 64 filters, and then we are going to input the shape which we want, and then you can use any activation functions. So you can maybe use 10 hyperbolic, softmax, ReLU, rectify linear unit, any function of activation function of your choice which is solving your purpose. And then we are going to use an optimizer. We can use stochastic gradient descent, SGD, and then we are going to choose learning rate, and to specify the loss function which we are going to use in optimizer, we are going to use it compile function. And this is the way if you were to implement RMSprop in Keras, and I hope it gives you better intuition on what's really happens whether if you are using any deep learning framework such as TensorFlow, Keras or PyTorch. I hope you like this video, and please give any constructive feedback in the comment section below. Please don't forget to subscribe. That's what keeps me going. Thank you and have a nice day.